Hello and welcome to another one of D's ADD videos. Today we're going to be looking at the concept of limits. We're going to approach limits one of three different ways. The first way we're going to look at it is graphically. So basically what we're going to do for a limit on a graph is look at the function, zoom in on either side of some x value, and see if it approaches the same y value. So when we're zooming on either side, the positive and the negative, we're going to end up approaching really close, but we don't care what's going on at the actual function value. I can have an open circle at the value and still have a limit. We'll see that here in a second. So let's look at some random function, whatever this function is, and let's take some limit as x approaches c of the function. Limit as x approaches c of the function. And here's our x equals c, so basically we're going to try to figure out if I zoom in from either side, does it indeed approach the same y value? Here, we actually see that when I approach, this is the notation for one-sided limits, so the limit as x approaches c from the negative looks like it's going to the same value that the limit as x approaches c from the positive is, right? They're both going right there. And we're going really close, but not actually touching x equals c. So the conclusion we can make is that the limit does equal L, because they approach the same value, the left equal the right. The left equal the right. So let's look at this function here. Some other function, doesn't matter what it is. I want you to take note here, we have an open dot. So if we were to look at the function and take the limit as x approaches c of that function, so we're looking at this, does the limit exist? Well, yeah, it does, because when we approach on either side, we're approaching that same L value. So the conclusion we would make is because the left limit as x approaches c from the left side, this negative sign means left, equals the limit as x approaches c from the right side. They both equal L, so therefore the limit as x approaches c equals L. Hopefully that's pretty straightforward. Do a few examples out of your textbook and you'll get the hang of it. Finally, let's take a look at an example where it doesn't exist. Well, here we have a piecewise function. And here we've got one piece defined by another function between these two values. I don't care about what's going on anywhere except for right here. Let's look at what's going on here. So if I look at x equals c, yes, the c value happens to be 0. That's fine. But I'm just looking in general. I should be able to visually notice that the left limit does not equal the right limit. One equals 4, the other one equals 5. So in that scenario, the limit as x approaches c, or 0, from the negative equals 4, which does not equal the limit as x approaches c from the positive, which equals 5. So therefore, the limit does not exist. Okay. When we talk about discontinuities here in a little bit, we'll find out that this is called a jump discontinuity. The one open dot we had earlier is a removable discontinuity. Now note here, it is a piecewise function, and we are continuous with these two pieces because there's no open dot there. Okay, and the limit does approach the same value from either side, so the limit does exist. Later on, when we discuss continuity, we'll also find out that those are the criteria for continuity. Function must be defined, the limit must exist, and the two must equal each other. That's another discussion, but I hope I've explained graphically clearly to you. Now let's look at the next way we're going to approach it, analytically. Both graphically and analytically, we're not going to use it too much. You might get it for the concept, be assigned a little here and there. All right, so analytically, what we're going to do is we're going to zoom in just like we did on the graph, but we're going to do it with a calculator and plug in some values. And notice my values are really close to the c value we're going to approach, where we want to go either side, 0.1, 0.01, and see what the pattern is as we get closer and closer to that x equals c. Again, in essence, we're going to be zooming in from either side to see if the one-sided limits are the same. This time we're going to do it with a calculator instead of looking at the graph. Let's look at the function f of x equals 2x. If we were to zoom in on either side at x, let's say x equals 1, for instance, then what we would be doing is approaching 1 from the negative direction. So we'd subtract 0.1, 0.01, 0.001, 0.001, get these x values. And then also do the same thing from the positive direction. And we're going to start with 0.1, adding 0.1, adding 0.01, 0.001. And you'll notice we're zooming in, getting closer and closer from either side to x equals 1. And if you plug into your calculator and look at the trend, this is what you'll get. And you can see that they're both approaching 2, no matter which direction I'm approaching from. So as a result, we can conclude that the limit as x approaches 1 of 2x equals 2. Now, algebraically, it's much easier just to plug in a 1. 2 times 1 is 2. That's an acceptable answer, and we move on. And that's why we rarely will do these tables unless we're trying to understand what's going on with limits. So let's look at the last way. The last way we're going to look at this is indeed algebraically. And what we're going to do here is we're going to look at plugging in the number like I just did with that 1 into the 2x. If you get a number, you're done. We got 2. I said we were done. That's good enough. That's easy. But if you get 0 over 0 or infinity over infinity, whether positive or negative on top or both positive and both negative, just infinite over infinite, then you're going to have to do algebra until you no longer have one of these forms. There's actually a few more. These are referred to as indeterminate forms, and we will spend a whole separate topic on indeterminate forms. But for now, we're just going to deal with these basic indeterminate forms. If you see these, do algebra or some trig. What can we do? Well, so you can either factor and cancel something, or find common denominator, something will cancel, multiply by the conjugate, eliminate the problem. The key is something has to cancel, or the thing that's causing you to be indeterminate has to no longer be indeterminate until you get a finite number. Okay, you can't have 0 over 0 or infinity over infinity anymore. Or you could get infinity as an answer. That's acceptable as well, all right? Or negative infinity, but not these two, all right? So check out the example videos. Primarily, I'm going to focus on the algebraic approach, okay? If we do some problems out of the book, I think the graphical and the analytic approach can be figured out relatively quickly. Just stay focused. More importantly, practice, practice, practice. Thanks for watching. Have a great day.